What if I told you there are truths out there, truths you know are true, but that you could never, ever prove? Well, in 1931, one man showed that these truths don't just exist, they're a fundamental feature of mathematics itself. This is the story of Gödel's incompleteness, a discovery that found a permanent crack in the very foundation of logic. So back in 1931, a quiet, 25-year-old Austrian mathematician, Kurt Gödel, unleashed this paper that just sent an earthquake through the worlds of logic and philosophy. He proved that even in something as simple as basic arithmetic, there are statements that are totally true, but impossible to prove. This, as one philosopher put it, created a scandal. Why? Because math was supposed to be the one place where everything was perfectly certain.
Okay, to really get what Gödel did, we gotta start with a classic brain teaser, the liar's paradox. Just think about the sentence. This statement is false. See the problem? If you say it's true, well then it has to be false. But if you say it's false, then it must be true. It's this little knot that logic just can't untie. And Gödel realized this wasn't just a fun word game. This idea of a statement talking about itself was the secret key. Now, to feel the full impact of Gödel's discovery, you have to understand the beautiful dream that he shattered. In the early 20th century, the biggest names in math, like the legendary David Hilbert, were on this grand quest to build a perfect, airtight system for all of mathematics, a fortress of logic that could solve any math problem you could ever throw at it. This whole dream, it rested on three huge promises. First, completeness, the idea that any statement that's true can also be proven. Next, consistency, a guarantee that the system would never, ever contradict itself. And finally, decidability, the belief that you could create a surefire method to decide if any statement was provable or not. It was this vision of a perfect clockwork universe of mathematical certainty. So this is where Kurt Gödel walks onto the scene. And instead of trying to build the fortress walls higher, he found this incredibly clever way to sneak inside and use the system's own language to check its blueprints. And his secret weapon? It was a kind of mathematical code. This secret weapon has a fancy name, arithmetization. But don't let the word scare you. Just think of it as creating a secret code for logic itself. Gödel figured out a way to translate every symbol, every formula, and even every proof into its own unique number. The sheer scale of this idea is just mind-blowing. First, every little symbol, like not, or, equals, got its own number. Then, he used a really clever method to combine these into these massive, unique numbers that stood for entire formulas. He even encoded whole chains of logic, entire proofs, into their own colossal Gödel numbers. Everything in logic now had a numerical alter ego. And here's the magic trick. This is the big reveal. By turning logic into numbers, Gödel made it possible for mathematics to talk about itself. A statement about whether something was provable was no longer just some comment from the outside. It could now be written as an actual mathematical equation inside the system. For the very first time, that fortress of logic could look in a mirror. So what did Gödel find when he held that mirror up to mathematics? He found a crack. He found a statement that would basically break the system's own rules about what it means to be true and what it means to be provable. And this all boils down to one crucial, mind-bending question. What happens when you use this new power of self-reference to build a statement that talks about its own ability to be proven? Or, more importantly, its own inability to be proven. And that is exactly what he did. Using his numbering system, he built a totally valid, rock-solid mathematical statement, we'll just call it G, and when you decoded its Gödel number, its meaning was, essentially, this statement cannot be proven. He had made a mathematical version of the liar's paradox.
Okay, hang on, because this is the heart of the whole thing. Let's walk through this trap he laid. Option 1, what if statement G is provable? Well, that means the system has just proven something that claims it's unprovable. The whole system is a liar. It's inconsistent. So let's assume the system isn't a liar, that it's consistent. That leaves only one other option. Statement G has to be unprovable. But wait, if it's unprovable, then this statement is unprovable, is actually true. And there it is. We have a statement that is true, but the system is powerless to prove it. The dream of completeness is shattered. And that mind-bending paradox, that is the core of Gödel's first incompleteness theorem. It's the formal way of saying that any logical system that's consistent and powerful enough to do basic math will always be incomplete.
There will always be true statements that are just beyond its reach, like mathematical islands you can see from the shore, but you can never ever sail to with the ships of proof.
Oh, but Gödel wasn't done. Not by a long shot. After showing that the castle of logic had rooms it could never enter, he delivered an even bigger blow. He showed that the castle couldn't even prove that its own foundations were solid.
This is Gödel's second incompleteness theorem, and it says that no consistent system powerful enough for arithmetic can ever prove its own consistency. You can't use the rules of the system to prove that the rules themselves are sound. To do that, you'd have to step outside of it and use a bigger, more powerful system. But of course, that bigger system can't prove its own consistency either, and so on forever. So was this whole thing a bust for math? Did Gödel just break it? No, not at all. It was actually this moment of profound insight. This isn't really a story about what math can't do. It's a story about the true nature of logic, truth, and certainty itself. The fallout from this was just massive. The grand quest for one perfect theory of everything in math was officially over. Gödel showed that incompleteness isn't a flaw. It's a fundamental feature of logic. He forced us all to see this huge difference between what is true and what is provable. They are not the same thing. And as ideas about what could be mechanically proven laid the groundwork for Alan Turing and the entire theory of computation, which is the blueprint for every computer you've ever used.
So we're left with this incredible thought. Gödel proved that even in the purest, most rigorous world of logic and numbers, there are horizons that proof can never cross. And that leaves us with a pretty deep question to think about. If even pure mathematics has these fundamental limits, what does that mean for our search for absolute, provable truth in the much messier worlds of science, philosophy, and our own day-to-day lives?